Hi, my name is Ryan Brooks, and I am the Principal Technical Artist at Epic Games. Today we're going to be talking about Fortnite and some of the ways that it uses new and upcoming Unreal Engine features. We will take a look at what it's like to use some of these tools to make changes inside the Fortnite world, and that should help give an idea of what the tools are capable of. And in some cases, we will talk about how these tools might apply for different cases outside of just Fortnite. Let's jump in. Before we talk about any specific tools, I'd like to talk about the role that we see tools playing in general, and that's to help empower artists and designers implement their vision into the engine. So some of our tools' goals are to help with consistency and managing of the boring stuff while streamlining the creative process. So with that in mind, what does this mean for Fortnite? Well, Fortnite has a unique set of development challenges, such as it has a large open world, it's frequently updated, and we want those updates to feel meaningful. The Fortnite map was pretty consistently updated every season between 1 through 10. Often large parts of the island were redesigned or changed to a new biome type, such as snow or desert. However, for Chapter 2, the development challenges were on another scale. We needed to create a completely new island while dealing with new tech challenges like a more diverse terrain with a gameplay interactive water system, all in a time frame not very different from one of our usual seasonal update cycles. And a quick disclaimer that Fortnite's world is still largely crafted with love by hand by our designers. The open world tools here are designed to help them get their vision into the engine more efficiently. So we'll start with the topic breakdown so you can hopefully find your way through this recording a little bit more easily. We're going to start with landscape. We're going to talk about the new virtual texturing system used in Fortnite, the new landscape layer system, the new landscape splines allowing non-destructive editing, and custom blueprint brushes. Then we are going to talk about the new water system. This is a new system coming in Unreal Engine 426 that allows integrated terrain carving and fluid simulation, gameplay interaction, including waves and flow maps. Next up, we will talk about how Fortnite is using the new Sky Atmosphere component from Unreal Engine 424, as well as give a quick preview of the upcoming volumetric cloud system that will ship with Unreal Engine 426. And finally, we will end by talking about some general editing tools. That includes things like placing objects in the world such as trees, roads, and buildings, or breaking up the world for streaming, etc. Really the bread and butter of level design. Some of the tools we will show are available in the engine today, and others are still a work in progress, but we wanted to show some early examples. Our first feature category is landscape. The first feature to talk about here is runtime virtual texturing. Now this is not strictly a landscape feature by any means, but in Fortnite we are primarily using it for landscape purposes. Before jumping into virtual texturing, I'd like to point out the distinction between two completely different types of virtual texturing systems in Unreal Engine. We have both the streaming VT and the runtime VT. The streaming VT, on one hand, is streamed from disk and generally saves memory at the cost of some performance, and is not currently used in Fortnite. The runtime VT, on the other hand, is generated by the GPU at runtime, and it saves performance at the cost of some memory, and it's generally beneficial for complex layered materials. It is now used in Fortnite as of Chapter 2. The streaming VT, which as before is not currently used in Fortnite, is basically a way to have more granular streaming of large textures. Different regions of one texture can be streamed in at different resolutions. This is basically just a texture setting on the texture assets and doesn't involve any sort of workflow changes or added capabilities beyond the increased resolution that you can load. The runtime VT, on the other hand, allows different objects, including both static mesh and terrain, to combine into one single virtual texture. This is ideal for very expensive multi-layered materials or where custom blend effects are needed. Now let's take a look at how Fortnite implements the runtime virtual texturing. The first thing required are runtime virtual texture volumes. These are volumes that tell the virtual texturing system how large each virtual texture needs to be in the world. Now in Battle Royale, since we have a lobby island so far away from the main island, we decided to give it its own separate virtual texturing setup, so as not to waste memory storing virtual texturing where we don't need it. And the second thing to note is that we actually have two volumes per virtual texture. One is the default virtual texture type, which includes base color, normal, roughness, and specular, and the other is world height, which includes the world height of anything inside the virtual texture. Here we see the main volume for the main island, and then the second volume for the main island, which includes the terrain and virtual texture height. These are the asset details for each of the runtime virtual texture assets. Notice the one on the left is set to base color, normal, roughness, and specular. This is like having a simplified material attributes set all in one asset. The one on the right is set to world height, which gives access to the height of anything in the runtime virtual texture to any material in the world that reads the RVT. This shows the implementation of virtual texturing inside of a terrain material. On the left, the material outputs to the virtual texture using the runtime virtual texture output node. This is what actually renders to the RVT. And then on the right, the virtual texture is sampled using the RVT sample target node. Downstream from this material attributes here, any custom blending effects can happen. For example, here we have a rock blending into the terrain seamlessly by referencing both the virtual texture material attributes as well as the RVT height. This shows the setup to get a material blend from the runtime virtual texture world height. First, we sample world position, the blue channel, or the Z, and then we sample the runtime virtual texture world height. Then it's a simple matter of subtracting them, adding a bias, and dividing by our desired length before clamping that result. And now we have an alpha that we can use to blend multiple materials. This slide shows the results of roads blending into landscape using virtual texturing. In this image, there's no road geometry shown. The road texture has been written into the runtime virtual texture and seamlessly blended into the terrain. Now in this slide, we're showing the geometry for the road on top of the terrain. It's not a very big change, and in fact, it's not really needed for rendering anymore. The only reason we keep it around is because the road collision gave nicer results and feel to the vehicle driving physics. And of course, if we're going to have the collision, we need to have the geometry match as well. This shows the wireframe of the spline mesh. A useful debug that the level designers on Fortnite added is the ability to look at the runtime virtual texture in a split-screen comparison mode. This basically allows outputting both the runtime virtual texture and original material using a split-screen blend. Here, we are visualizing the split-screen comparison. On the left, we're showing the virtual texture on with the seamless blend to the terrain, and on the right, the virtual texture is off, showing the geometry itself with a separate material and no seamless blend. Let's go ahead and take a look at the differences in shader complexity with the virtual texture on and off. So we'll be looking at the whole island from an above view. With the virtual texture disabled, we can see a fairly high shader complexity. Now these red values start around 500, 550 instructions. In those sections of pink we see over the water, somewhere over 1,000 instructions. With the runtime virtual texture enabled, we have much lower shader complexity and a much more consistent result. We don't have some terrain components with a higher complexity because they happen to have more layers painted. For reference, green indicates an instruction count around under 200. Now for performance, we don't have exact metrics for you today, but we have some approximate cost benefit on the PlayStation 4. It costs us roughly 1 millisecond to update the runtime virtual texture, but in a typical view with a lot of terrain on screen, it can save us around 3 milliseconds. And that's view dependent. It goes up a lot when we're in the skydiving view covering the whole screen with terrain, and it goes down obviously when indoors and not looking at very much terrain on screen. Another useful debug mode is to display the runtime virtual texture output level. This is kind of like looking at the MIPS of the RVT. This is built into the Fortnite terrain material as an optional debug display mode, shown here. The next landscape feature to discuss is the new landscape layer system. This adds a stack of landscape layers where each layer contains a full terrain dataset. That means a set of height maps and weight map layers in each layer that you add. The layer stack adds flexibility, and it's great for transient work and testing one-offs or doing changes that might need to be undone in the future. This video shows what it's like to work with landscape layers. Notice in the landscape tool, we now have an edit layers group with different layers. Here we have a base layer forming the general shape of the island, and then we have a details layer on top, allowing additional modifications. Now we can paint changes inside of this detail layer and then toggle them afterwards to see the terrain without those changes. And one of the great things about these layers is you can simply erase a layer that's higher up to reveal what was beneath in the stack. So if you needed to move those buildings somewhere else, you don't have to worry about the fact that you destructively flattened out the terrain underneath the building. You can just erase those layer edits. So that's why it's great for things like integrating man-made structures into a natural terrain. And you can also, as shown here, perform smoothing and other features inside of a terrain layer. Next, we're going to be talking about the new landscape splines. These allow us to non-destructively carve the terrain. And these are actually built into the new landscape layer system. In the previous video, you might have noticed that there was a splines layer that was grayed out, and that's because the new landscape layer system reserves a layer for splines if you so choose. And this video shows what it's like to work with the new non-destructive landscape splines. We select the landscape spline layer, and by holding Control and clicking across the landscape, we add new spline points to our road. Notice that as we add points, the terrain is non-destructively carved in real time. Going to apply a road mesh so we have something a little bit more interesting to look at. And now we can select spline points, and as we move them, the results update the non-destructive carving immediately. This is really useful for making small tweaks without having to erase and try redoing over and over again and destroying your previous work. The landscape splines can also write to weight map layers. We can toggle the effect of the landscape spline layer just like the other layers. Custom blueprint brushes is another feature that was added along with the landscape edit layer system in 424. These are material-based terrain modifiers that use the GPU to generate data. Under the sculpt and paint modes of landscape, there is a new blueprint brushes tool. This is how you select and add brushes. Brushes in the world show up in the list on the right under edit layer blueprint brushes. An experimental plugin called Landmass offers some flexible example brushes, but you can also derive from the parent C++ class to make a custom brush from a blank slate. The class for that is Landscape Blueprint Brush. The image on the right shows the default brush types included in the Landmass plugin. This is an example of the kind of flexible effects that are possible with the custom brush system. Use shapes to define biomes and manipulate the terrain in various ways. Both height maps and weight maps can be modified, and the brushes can be defined in countless ways from splines to static meshes as inputs. This slide shows an example of the data flow from landscape to custom brushes and back. Landscape initiates a render function on a custom brush with the current terrain data as input. The brush then performs GPU material renders using this data, which results in render targets as output. These render targets are then passed back to the landscape. This is an example implementation of that render function inside of a custom brush. The current terrain data will be supplied, which can then be modified using a material and written to a render target. Then that modified render target is returned back to the landscape on the return node. The output of a custom brush is completely customizable, but here is a look at how the Landmass plugin generates terrain formations from simple shapes. The data flow involved is to first generate a mask of a shape defined by a spline. An edge detection pass is then run on this mask, which stores edge seed locations. The jump flood algorithm is then run on the seed locations to generate a Voronoi diagram, which can be converted into a signed distance field. Noise can be added to break up the shape inside the seed by adding noise to the seed locations. This is just an example of how the distance field from a spline can generate different terrain shapes. Different effects result from capping the interior and raising or lowering the brush. This video shows a prototype of a shape drawing method that Landmass uses. Presets like mountain, landmass, road, or river can be selected and drawn, and then the points can afterwards be selected and modified as normal. Since custom brushes exist in a stack, the stack can be reordered so different objects have different priority. If we put the canyon higher in the stack, it will carve out the mountain. If the mountain is higher, the mountain will fill up the valley instead. So one caveat about custom brushes is that they are not currently used in Fortnite yet outside of some experimentation. But they did form the basis for part of another system that we're about to talk about next, and that's the water system. For more detail on custom brushes, you can see the talk Unreal Engine Open World Preview and Landscape Tools from Unreal Dev Days 2019. And now for a topic that I've been waiting for a long time to talk about. Water was one of the biggest new additions to Fortnite in Chapter 2, and we are excited to be bringing the set of water editing and interaction tools to Unreal Engine in 426 as a unified water system. The water system lets you define lakes, rivers, oceans, and islands using splines. It includes gameplay interaction and fluid simulation. The image here shows how we broke down the water object types for the initial version of water in Chapter 2. At the core of the water system is a new water spline type. The water spline allows customizable water properties to be edited at each spline point with interactive visualization gizmos. This means we can adjust things like the depth, width, velocity, and audio parameters of the river at each point. This video shows what it's like to work with the water body system. Water bodies are actors just like any other in the world, and they can be manipulated, scaled, rotated, or duplicated. So we can take this river here and alt drag it out to make a copy of it and see how it might look somewhere else in the world. We can use that as a foundation to form another river, for example. Or we can take a piece of a new river that I created there and alt drag off one of its points to create a fork in the river. And we'll have this fork go ahead and extend out to meet the ocean. And on the right on the details panel, you'll actually see some of the terrain carving settings of the water bodies, which come from the landmass plugin that was mentioned previously. So the first thing we'll do here is select these water points and move them down flush with the ocean, because while the system does blend the velocity and height, you still want to get the height of the river to be close to the ocean. Now what we did here is select and show the river width gizmo. That allows us to select and modify the width of the river at each point. And then here we chose to modify the edge offset of the river to give a little bit more of a shore width. So the next visualizer we'll show here is the depth visualizer. So that adds a new little gizmo under each spline point that we can select and then drag to modify the depth of the river at every point. So I'm going to go ahead here and modify all these points to get the river to be a little bit more shallow. And then finally we're going to show the last visualization type, which is velocity. When we turn on velocity, we get these new arrow gizmos that we can click and drag to increase or decrease the velocity. And the material is automatically set up to render and generate flow maps for the whole world, which allows us to see foam in the river as we modify it. And then that also has an impact on both the gameplay and the fluid simulation. So now that we have these river points looking pretty decent like we wanted, we might want to maybe change the slope of the terrain outside of the river. We can do that as well using some of the terrain carving options. So now we'll look at how the velocity texture is generated. We render a combined water texture atlas, which includes all of the water information for a single terrain. This includes water velocity, water height, and terrain height. This unified texture is very useful to have for water materials and simulation purposes. The velocity has a built-in flow map based on the spline data, and that's what's used to generate the white foam that we saw in the previous video. To render all this water, we needed an efficient and scalable solution. We wanted a detailed surface up close, but we also needed it to run fast, so it needed to simplify aggressively in the distance. This is handled by the new water mesh actor. The water mesh actor builds a quad tree grid around all water features, allowing detail up close and simplification far away, with smooth transitions in between. This example shows how the quad tree grid refines with distance and gets more detailed as the camera approaches the surface. Since we have a global water texture, it's possible to render the whole water surface with one shader, but this wouldn't be ideal for performance. For example, oceans and lakes have waves, while rivers have flow maps. It would be a bit wasteful to pay the cost of flow maps on the whole ocean. We separate the functionality unique to oceans, lakes, and rivers into separate materials. We then expose transition types that enable blending between those materials. Transitions are always between rivers and oceans, or rivers and lakes. Transitions are the most expensive material types. This shows a debug mode of the water mesh tiles from the water mesh quad tree. The tile color shows the type of tile. Blue represents ocean, green is for lakes, and red is for rivers. Purple represents a river to ocean transition, and yellow represents a river to lake transition. Note that we also fade out the water using the water depth texture to prevent water geometry from clipping. Notice that the swamp is green even though it's at ocean level. This is because we nested a lake into the ocean and used that to restrict the swamp's additional material complexity only to the swamp region. With all this detail, we can now render some pretty nice waves. We decided to implement Gerstner waves, which are a well-known analytical wave formula that is based on sine waves. They are useful for being able to easily match the same result on the CPU and GPU, so that gameplay and rendering can both match each other. This video shows the effect of combining 16 Gerstner waves together. Once you get to this number of waves, it starts to build a pretty realistic water surface. But of course, Fortnite is stylized, and we don't necessarily want to be too realistic with our water. We found a solution there by limiting the number of waves and carefully controlling the wave parameters. Fortnite only uses 6 waves, and mobile is further limited to 4 waves. We sort the waves from biggest to smallest, so that the 2 waves dropped on mobile are the smallest 2, and do not have much impact on the gameplay visual match. Each water body has its own set of wave parameters that we refer to as a spectrum. This gives a range of values for things like amplitude and wavelength, and the distribution between values. This is just an example of how 2 water bodies near each other can have completely different wave spectrum values, the one on the left having moderately choppy waves and the one on the right having almost no waves. This video shows what it's like to edit the wave spectrum values for the Fortnite ocean. First, we will set the number of waves to 0 to show a calm ocean. Then we will slowly re-enable the waves one at a time. You can see how each wave after the first few has a relatively small impact, but they still help in the final result. Next, we can adjust the amplitudes to make the waves larger or smaller. We have to be careful to test after playing with these values because the waves tend to look a lot bigger from the player perspective. Adjusting the fall-off allows you to adjust the distribution between your small and large waves. This lets you say whether you'd rather have more of the small waves, more of the large waves, or an equal distribution if the fall-off is 1. And the same goes for wavelengths as well. We typically use a wavelength fall-off of somewhere around 3 or 4 because we tend to want more of the small waves versus more of the large waves. We can also adjust the wave steepness. The dominant wave direction determines the direction of the first and largest wave, which is also the starting point from which all the other random waves are generated from. You can also adjust the amount of angular random spread for those secondary waves as well. To help improve the quality of the water rendering, a new shading model called Single Layer Water has been added. This has already made its way into the public release in 4.24 actually. This adds a single layer water material node to the graph that allows colored absorption based on depth, as well as scattering and anisotropy controls. The water renders as opaque and is rendered in a separate water pass that performs screen space reflections. This screenshot shows the benefit of having colored absorption, screen space reflections, and standard material controls like roughness and specular all working properly together now. And our last water topic is fluid simulation. The water system includes a built-in fluid simulation tool that allows character, vehicle, and weapon interactions. The fluid also responds to the terrain, such as reflecting ripples off the shore and being affected by river flow maps. This video demonstrates some of the fluid interactions in Fortnite. Weapons and character movements disturb the water and the foam on the surface of the water. The simulation is performed in a local range around the player, and it can be affected by a set number of other nearby players as well. The simulation can also be affected by the river flow maps that are generated by editing the water spline points. This causes the ripples to flow downstream, as you would expect. Here, a debug command is entered to show the character fluid force. We basically draw a stick figure shape by supplying bone locations and rendering them as capsules in a material. Boats use a simpler fluid force type that is a simple texture-based shape defined by an effects artist that is attached to the boat mesh. With the boat, we can cause much larger ripples and clear larger paths in the foam. The fluid simulation helps add to the feel of the player interacting with the world as they drive the vehicle. Here we take a look at how the foam erasing effect is done. Our fluid sim actually has 2 channels, a red channel and a green channel. The red channel is a standard fluid solver. You can actually find a similar example in the Content Examples project by loading the blueprint render to target map. For the green channel, we perform a diffusion or a blur step that has a minor feedback from the red channel applied. This green channel is then used to subtract from the opacity of foam in the water. The swamp biome also makes interesting use of the fluid diffusion channel by making moving objects clear a path in the pond scum. This can provide some visual interest when wading through the swamp as a player, or driving through in the boat. It also uses the same method to create a glow effect in the slurp juice that is spilled throughout the swamp. And now we will talk about sky and atmosphere. As of 424, UE4 has a new robust sky atmosphere model. It's a multi-bounce Rayleigh scattering model, and while it's physically based, it's still highly art directable, which was a big requirement to be able to use it in Fortnite. And it also scales all the way from high-end PCs down to mobile devices. And as of Chapter 2, Fortnite is now using the new sky atmosphere. Now it's worth pointing out that physically based doesn't have to be boring. And what I mean by that is, you can still just use it as a starting point for your artistic expression. I'd like to share my own experience when I first started learning about physically based rendering for materials when Disney first popularized it years back. Initially it sounded both very cool and a bit intimidating. At the time, making materials look nice was basically what tech artists spent time doing, so it felt a bit like PBR was going to take that away, so to speak. In talking with other tech artists, I wasn't the only person who brought up that fear. It was a vague sense that we might lose some freedom or some expression. In reality, the exact opposite happened. Now, because of PBR rendering taking over, there are so many more jobs and things for tech artists to do in the field compared to before, and people are tackling bigger, more complex problems instead of all resolving the same basic problems. The same thing will likely be true in other areas in the future, such as skies and atmospheres. Fortnite uses a time of day manager blueprint to manage the sky atmosphere values. Our time of day blueprint has 4 values for time of day. We have morning, day, evening, and night. Each time of day has a separate struct with a group of parameters, controlling multiple actors like the sun, the sky atmosphere, and the height fog. For the sky atmosphere, this lets us change things like the Rayleigh and my scattering colors at each time of day and fine-tune that interaction with the lighting and the fog together. Controlling each time separately allows artistic control as a layer on top of physical basis. Here we see the effect of scrubbing the time of day preview inside of the editor. We can see how, even though this is a physically based sky, it still manages to look fairly stylized with nice artistic and stylistic colors. And here we disable the height fog, and now disabling the atmosphere. So you can see we still use an exponential height fog, and together the height fog with the sky atmosphere really forms the total atmosphere that we now have in Fortnite. We have another exciting new feature coming in 426, and that is volumetric clouds. GitHub users can access it using dev rendering. The volumetric cloud system was used in the Fortnite Chapter 2 Season 3 cinematic, as well as the recently shown PlayStation 5 demo alongside our new nanite rendering technology. The volumetric clouds use the material domain called volume. This lets users specify their clouds with a standard material interface. This is an example of an extremely basic cloud material. The cloud mask logic should go into the extinction pin. This graph here just maps a simple tiling 2D texture across the sky. It then subtracts a bias and multiplies by a density parameter. Next, we will see what it looks like and what it takes to make it look like a proper cloud material. We start by showing the volumetric cloud actor. The actor has some basic controls for things like the thickness of the cloud layer, which we're adjusting here, as well as the starting altitude of the clouds. And so far this material is just the simple tiling circle we saw, but we can open that material instance and adjust the bias parameter to erode the shape to make the clouds either larger or smaller. Now let's take a look at the material and improve it. Here's where we left off from the previous slide. If we scroll down a bit, there's a function for controllable height falloff. Cloud materials have access to a node called Cloud Sample Attributes, which was just selected, which gives access to the normalized height within the cloud layer. This can be used to map falloff functions. This is a simple exponential falloff for the top and bottom. We can now go back to the instance and scrub these values to play with them and control them each separately to create different types of shapes. Now let's go back to the material and add some detail. To do that, we're going to add a volume texture. So here we have a texture sample of a volume texture, and it just has world coordinates multiplied by a tiling factor and controlled by a multiplier for the density. Then we compile and go back to the material, looking at it, and now we have some detail making some cloud-like edges, and we can adjust that detail parameter. Notice it can be either positive or negative for some different types of effects. So now we can go beyond that, and instead of just using a tiling 2D circle texture, using a texture that has more of a natural noise in it. So now compiling the shader with the noise material, we're going to have to adjust the tiling a little bit to get something reasonable. So we'll go ahead and adjust the density and the tiling really quick. And then we start to get something that looks a lot more like a procedural sky generated just from some tiling textures. So now when we get something closer to where we want, we can start to play with the time of day and see how we did. So you can also get creative with defining the clouds. Here's an example of a texture mask being generated from a curve, so you can define the height profile of the clouds more directly. And then of course you can take that same approach from the previous section and apply a tiling noise volume on top to break up the surface and create a realistic shape that has detail as well as a nice macro shape. And this video shows a blueprint being used to generate a cloud mask by positioning individual actors. As the actors are moved, the cloud mask is updated, which you can see here in red in the lower right. This is done by drawing materials to a render target. Each cloud object has its own settings for scale, noise, opacity, and others. Here we scrub the seed of the noise to try some different looks. We can also quickly duplicate a single cloud around the scene to compose a desired view. It can help to place some larger clouds on the horizon, and use the noise settings to create a large cluster to easily shape large regions of the sky at one time. So now that we've positioned some clouds roughly how we want our scene, let's go ahead and start moving around the sun, which we can do just by holding Ctrl L and moving the mouse, which is another nice new feature that came along with the sky atmosphere. So you can see we're able to get some pretty nice results just from dragging a handful of actors around the scene. And then of course we might decide we want to add some more clouds just for this other sunset view over here, and that can be pretty satisfying as well. And of course, you're not limited to realistic clouds either. This is an example of a stylized test showing the flexibility of the volume material, which means you can try non-realistic rendering as well as pretty much anything that you can imagine. And now we have reached our final category, general editing. And we will start with grid-based editing. This is a new tool to help automatically partition the world into a grid, similar to how the Fortnite in-game minimap is divided into grid cells A1 through J10. Grid-based editing will automatically ensure that actors get placed into the right sublevel. This feature is still a ways out from release. For now, similar results can be achieved using the World Composition tool and its Tiled Landscape import feature to help create a grid. This is a debug display of what it's like to move an actor around with a level grid. When an actor is moved outside of its grid cell, you can see a new level is chosen, which is displayed as a yellow square in this debug view. Previously, if you accidentally moved an actor outside of its intended level grid, this could have caused a streaming problem, requiring a level designer to manually fix up. Another upcoming feature to help with this sort of editing is one file per actor. This is coming in Unreal Engine 426. This is a new file and source control paradigm, and while it's not used in Fortnite yet, we expect to be using it soon. What this feature does is allow an object's outer to be defined by another package. This is in an effort to reduce file contention. So what that means is when you have actors stored in a level, as is the traditional method used now, only one person can check out that level file because it's a binary file. You can't merge different binary edits like you can with code. So what this might mean here, if you have a section of the world with different types of objects like trees and houses and terrain, typically only one person is going to be able to check out that area and work on it at a time. With one file per actor, since these actors all become separate files, pretty much anyone can check out what they need to work on as long as they don't need to work on the same exact objects. Another useful feature that we added to help with the development of Fortnite is actor foliage. And what that allows us to do is paint down blueprints just like they were static meshes with the foliage tool. And to do that, it's pretty simple. You just create a new actor foliage type, shown here how to make from the content browser. And it's worth pointing out that in Fortnite, very few objects are just regular static meshes. Pretty much everything you see in the world is a blueprint that allows level designer customization. So this means that previously, almost everything in the world had to be manually placed by duplicating or dragging from the content browser, which was a little bit tedious for level designers. And now we can basically paint down actors like they were foliage. This shows an example of what it's like to paint down actor foliage in the Fortnite map. Like before, we go to the foliage paint tab and we see our selection of foliage that we've added to be able to paint with. When we select one, we can see that it's now able to specify an actor class. So we can just click down and paint these. And another new mode that's being shown here, which is really useful, is the new single instance mode, which means you can place a single instance with a click without having to worry about getting the density just right to where either you wouldn't get trees or you would get trees. Because the traditional foliage paint was more meant for, I think, painting down more density than single objects, but it's still pretty useful to be able to plop down trees and objects with single clicks around the level like that. This was definitely requested by the level designers and allowed them to use the foliage paint tool, whereas previously they weren't really getting much out of it. So the next feature to talk about is improved hierarchical scattering. This adds better procedural scattering variety. Large objects can essentially act as anchor points and spawn smaller objects of a different variety. So Unreal Engine has had procedural scattering for a while now, but you couldn't really have different nested levels or have any hierarchy. This is a debug view showing what it's like to spawn objects using a landscape mask and have different types of objects spawned as children. As we get closer, we can actually see that the cylinder objects are spawning smaller sphere objects. Just an example of different things you could do, including large rock spires able to spawn smaller pieces of rock scree. And we've been looking forward to finding ways to use this in Fortnite upcoming as well. So that concludes this talk. Thank you all for listening. We look forward to seeing your feedback and all the things you guys create with these new tools. Thanks again.